So today's session will be more in the practical aspect of how the design of the electric motors and everything in this nature. So let me introduce Professor Kannan to you. Kannan is an alumnus of IIT Madras and is currently working as the Professor of Practice at the IIT Madras, where he leads a team of designing and developing high-efficiency traction motors for electrical vehicles. He is the founder and director of ATAL Foundation, a one-of-a-kind ideas accelerator, focused on bringing new technologies to the market, including microspin and skillberry. In addition, Kannan's passion for innovation-driven engineering led him to co-found and direct several tech companies like Vortex Engineering and Motors Design and Manufacturing. He serves on the board of Vellicro, a non-profit incubator Centroid Designs, a design services company, Sunbeam Chain of Schools, and PPSC Foundation, exploring the intersection of science and society. Kannan received the Distinguished Alumnus Award of the Indian Institute of Technology Madras in 2014 in recognition of his innovations and transformative work in sustainable solutions for the rural environment. So I request Professor Kannan to take over the sessions from now on. Can you hear us? Professor Kannan, am I audible to you? Dr. Kannan, can you hear us?
He's not able to hear you.
I think there may be some technology issues. He is unable to hear us probably. Professor Kannan, are you audible to you? We cannot hear you. I think there are some technical issues.
Yeah, can you hear me now? Hello?
Yeah, I can hear you. Yeah, I can hear you.
Fine, thank you.
Good morning, Professor. Yeah, so we are about to start your session, so you can take over from now on and take the session. Okay.
Fine. So, good morning, everybody. Are you all charged up for the session today? I'm not hearing the roar. So maybe I'll just take a poll.
Yes, sir. Yes, yes.
Start up with the interaction and unmute yourself. That will be the best solution.
Yeah, I have with me my colleague Neetu. Neetu, your video is not on. Can you hear Neetu?
Yes, I'm having problems with my videos.
Okay. Can you do a poll?
Yes, sir.
Neetu?
Yes, sir.
So I think the question I want to ask all of you, since we are all in this mode, is I'll poll for your response to find out whether all of you are charged and raring to go. Neetu, you can show the poll.
Yeah, 1 second. The poll panel is not available to me anymore.
Huh?
The poll
let us just resolve all these.
Yes.
The panel is not enabled?
It was enabled until now, but it's not coming now. Could you grant me the presenter privileges again?
Just a moment, let me see if. Yeah, for me it's showing.
It disappeared from me.
It is showing up.
I don't have the call panel.
So are you all able to see anything like a poll on the screen? You can't see it?
The poll is visible. I think everyone is able to see it.
Yes, sir, we can see your poll.
So just select your answer, yes or no.
Sir, only one question. Is it
Only one question I've asked.
yes, sir, we are submitting.
See, today's session is going to be what is called a flipped classroom. A flipped classroom means that the students do all the work and the teacher is only there to facilitate. So you will all be doing most of the action. And what I am seeing is that 25 people have answered yes, 3 have answered no, and a fairly large number of people have not answered. So what's the problem? You're all not still awake? Still nursing a hangover? I want all of you to come pat with responses, and you have to be all very alert and on your toes. Here, I'll close the poll. When I close the poll, it still takes its own time to close. Anyway, doesn't matter. So let me go on. I had shared some video lectures. Did you all get to see it? There were, I think, about 17 videos that I had. Knowing what the content of the videos is and having an understanding of them will be important for you to participate in today's and tomorrow's sessions. So the question I would like to ask is, how many of the videos have you all seen? Because based on that, I'll have to pitch the level of difficulty. So Neetu, can you do a poll? Are you able to access the poll?
Not yet. I'm trying to get my percentage of wages restored, but I don't have it yet.
You're not able to.
Not yet.
For
I
the
think
polling?
when I got logged out and then logged back in, I lost my percentage of wages. So I'm working on it. I'll get back to you when it's restored.
Okay.
Morning, sir. Dear Srinivasan from JNT Kalkari, sir. It is not accepting the poll, sir.
I have now stopped the first question that I had polled for. See, a lot of my question in the form of interactive questions. So it's very important. I think Dr. Bhattacharya should resolve the issue because it's really mostly about things that all of you participants will be doing, less about what I will be talking. Did you all get the link for the videos?
Yes, sir.
You can
Yes, sir.
probably respond in the chat window also, since the poll is not working. Because in the original mail, the video link embedded in the mail was correct, but there was another wrong email given in the bottom, wrong link given in the bottom. So some people got confused by that. So good. A lot of people are saying that they got the link for the videos. Thank you. And how many videos did you manage to see? There were totally 17 of them. So can you? Okay, somebody says we saw 2 videos. Did anybody get past more than 2 videos? 9. Okay, that's a good number. Somebody says I got only a PDF and Excel. No, there was a link shared in the earlier email where there were a number of video lectures, about half an hour each, that were listed. Okay, so most of you have not gone past the first 2 videos, okay. Whereas there are 17 of them. Maybe what I will do is I will very quickly try and cover the content of the videos. I will go through it very rapidly because this is not meant to be a lecture session. It is more an interactive workshop and problem solving session. But since there was some confusion with the mail link and probably many of you may not have had enough time, I will very rapidly go through, and many of you are, I mean, all of you are faculty. So I will take the liberty of going quickly, but please feel free to stop me wherever you need a more detailed explanation. So don't hesitate to ask me to stop and explain something in greater detail. But if you don't stop me, I'll probably, there are something like 150 slides. And even if I take 10 seconds per slide, how many minutes is it? How many minutes would it extend? If there are 150 slides and I take 10 seconds per slide. I'm not finding any answers in the chat window. 1500 seconds. Yeah, how many minutes is it? Yes, 25 minutes. So we'll be ending up spending half an hour if I go uninterrupted. But if you need me to stop and explain in greater detail, please do. I don't mind spending an hour also on it or more, because it is important that you understand the basic concepts properly. So let me try and share my screen. Are you all able to see the screen?
Yes, sir, it is visible.
Great. Okay. So I will. This is actually a NPTEL course that we are offering from IIT Madras on electric vehicles, in which one section is about motors and controllers, which I have delivered the lectures for. And the slides that I'm showing you now, I have already shared them in the form of PDF. So all of you would have got it in the form of 4 separate PDF decks. So let me just run through it. So when I talk about motors and controllers, the important thing is that within a motor, there are things like there is electricity, there is magnetism, there is heat. A number of things are circulating and interacting with one another. So I have tried to summarize all of these in the form of by using the term flow. And whether we apply it to heat, whether we apply it to flow of air, flow of water, flow of current, flow of magnetic field, the underlying principles are similar. So if we understand flows, any one flow, if we understand, we can generalize it to all flows, and then the interactions between them is what finally determines the behavior of a motor. And there are only 3 things that define any flow. One is Ohm's law, where I'm having my window partially obscuring. One second. Okay. So there are only 3 rules governing all flows. The first of them is Ohm's law, where we say that the thing that is causing the flow, which is called the head in the case of water, voltage in the case of electricity, and many other analogous terms in other flows, is proportional to the thing that is flowing. In the case of water, it is the liters per minute that is flowing. In the case of electricity, it will be proportional to the amperes of current that is flowing, and so on. And the ratio between the two is the resistance that the path of flow is offering. And this resistance depends upon the material property and the geometry. So the geometry is typically described by length and area. And the material property is defined by a term called rho, which is a resistivity. And sometimes we use the reciprocal of rho as conductivity. Now, if I use this, and then there are 2 other things, Kirchhoff's first law and Kirchhoff's second law. Kirchhoff's first law says that whatever thing is flowing is conserved. It is the conservation of mass. So at any one junction, if there are a few paths that are flowing in and some paths that are flowing out, whatever is flowing in must flow out. If it is not, then either the thing that is flowing is disappearing, or it is being created out of nothing, and that's not possible. So that is Kirchhoff's first law. So you can see here that water is flowing through a network of pipes. Q1 is 3 liters per minute, and there are 2 outlets. One is Q2, which is 5 liters per minute, and the question is, what is Q3? And as you can see, what is flowing in must flow out. That means 3 is equal to Q2 plus Q3. And that will mean that Q3 is -2. And -2 means water is not flowing out, but flowing in. This is the idea behind first law. I don't know how I will know if any of you have a question. Is there a quick way for me to find out? Without exiting the window and looking at my chat, I don't know. Perhaps Neetu can look at it and pause me if anybody wants me to pause and explain. So that sum of flow at any point is 0 is called Kirchhoff's first law. In the case of in fluid dynamics, they call it the continuity equation. And then I move on to the second law. The second law is like conservation of energy. The thing that is causing the flow is the potential head, and if the potential field is conserved, which means energy is conserved, then the change in potential does not depend upon the path. No matter which path I take, the potential difference will be the same. That is Kirchhoff's second law. So as you can see, if I look at 2 points A and B, I can travel the path from A to B either by going through the middle path, or by taking the path on the right, or by taking the path on the left. No matter which path I take, the difference in head or the difference in potential between A and B will be the same. And I can use that knowledge to arrive at an equation like this. VB minus VA is the difference in potential that happens when I travel from A to B. And each of the paths will give me these equations. And by solving the equation, and in addition applying first law, which says that, for example, at this point, what is flowing in is Q1 and what is flowing out is Q2. And what is Q1, I mean, the amount that is flowing in should be equal to what is flowing out. Therefore, Q1 is equal to Q2. And likewise, I can apply the first law at this point, and I will know that Q1, which is flowing out, will be equal to Q4 plus Q3. And by using these relationships, I can solve and find what is the exact amount of water flowing in liters per minute in each of the tubes in this network, each of the pipes. So this is the second law. I will not go into these questions right now. Perhaps, yeah, the picture here just says that without knowing formulas for what is the resistance when resistances are connected in series, or what is the resistance when resistances are connected in parallel, if we just know Ohm's law, Kirchhoff's first and Kirchhoff's second law, we can actually figure out all these relationships. So we will discuss a little bit more about electricity. Now I'm coming to each of the different flows that are relevant to a motor. In the case of electricity, I is equal to V by R, familiar form of Ohm's law, where R is equal to rho into L by A. Now the interesting way in which I'm rearranging this equation, and we will do it repeatedly for all the flows, is because I don't want to mix up the material property and the geometry property. If you see the equation above, rho is the material property and L by A is related to the geometry. But when I want to compare different materials, I don't want to be distracted by the geometry. For example, if I'm trying to see whether copper is a better conductor or a worse conductor than aluminum, then if I just take two wires, one made of copper and one made of aluminum, and check the resistance, I may find that the aluminum wire has a lower resistance. But that is possibly because it's a very thick wire and of lesser length. Whereas the copper may show a high resistance because it's a very thin wire and a very long wire. So if I want to remove the distraction created by the geometry and only compare material versus material, then I will rewrite this equation as J equals sigma E, where sigma is the reciprocal of the resistivity 1 by rho, and J is the current density, which is I by A, and E is called the electric field, which is V by L. And then you can see that these two equations are equivalent. And now if I take J equal to sigma E and compare two materials, one of them is copper and the other is aluminum, then I will get a graph like this. The red line is for material number 1 and the blue line is for the material number 2, and whichever is having the higher slope has the better conductivity. So this will give me a clear understanding about the material without being misled by the geometry. And we will do this for many other flows as we go forward. So just keep this in mind. And meanwhile, Neetu, you must let me know if there are any questions that people are asking in the chat. And I'm moving on.
Nothing yet, sir.
Okay. Now I'll apply a similar concept in the case of magnetism. Now magnetism is something that many of us are less familiar with, but it behaves exactly like electricity. When there is a coil with some turns and current flows through that coil, then a magnetic flux is created. The flux is somewhat like water flowing through the pipe, or in the case of electricity, current flowing through the conductor. In the same way, through the coil, a magnetic flux is flowing, and that flux is equal to F by R, where F is called the magnetomotive force, which is nothing but the current multiplied by the number of turns. So its units is ampere turns, and the R is not resistance, but there's a slightly different name for that R. It is called reluctance, what you are seeing here on the bottom. And reluctance again can be expressed very much like the way we expressed resistance. It is 1 by mu into L by A, where mu is called the permeability. Just like you had sigma as the conductivity, you have mu here as the permeability. And usually we express permeability as a ratio compared with vacuum. When we do that, it's called the relative permeability, mu R. So the actual permeability of a material will be the permeability of vacuum multiplied by the relative permeability. Just like in the case of density, we compare with water, it's a relative density. So this is one thing. And the same modification to get rid of the geometry I'm doing again. I'm going to take the area factor which is there here along with the phi, then I will get a term called phi divided by A, which is the flux per unit area, and that is called the flux density. What you see here to the left hand side, B is the flux density, and its unit is called Tesla, whereas flux has a unit called Weber, and F divided by L is called the field strength, denoted by H. So we get this famous relationship called B is equal to mu into H, just like you had J equal to sigma into E in the previous slide in the case of electricity. Here you have B equals mu H. And just like in the previous slide, I can again draw a graph for comparing two different materials by plotting the B versus H. And you will expect to see a graph similar to the two with two different slopes, and whichever material has a higher slope, you will say has a higher permeability. But when we try to do this, we get into one problem. The normal non-magnetic or a poorly magnetic material behaves the way we expect. It's a straight line. But if I have something like magnetic or electrosteel, it is called electric steel, then the slope is very high, which means it has a very high permeability, but only up to a certain point. When the flux intensity, flux density crosses a certain threshold, the slope starts coming down, and finally it becomes as poorly permeable as a linear material. And this phenomenon is a very important phenomenon. We'll encounter it again and again in the case of motors. This is called saturation, and this saturation will significantly affect the behavior of a motor. So I want you to keep this in mind. And an example of what the impact of the saturation is that when I start from zero magnetizing force, which means I'm not passing any current and there is simply a piece of electric steel which is not a magnet. And as I start increasing, the dotted line shows how it increases. The interesting thing is, after I reach a certain threshold of flux, the slope becomes poor. And at that point, I say it has saturated. Then if I start bringing down the current going through the coil, it takes a different path. It doesn't come back in the same path. So you see that it will come down like this. As a result, when my current is completely switched off, it still retains some magnetism. That's called the retentivity. It's a retained magnetism. So what started off as a non-magnetic piece of iron, after I magnetized it to saturation and then switched off the current, it still retains some magnetism, and that's called the retentivity. And if I want to completely demagnetize it, I must now send the current in the opposite direction in the coil, which means I'm applying a negative magnetizing force. And when a sufficiently strong negative magnetizing force is applied, that is when all the magnetism will get flushed out, and the strength of the negative magnetizing force that is needed is called the coercivity. And then I can continue in the same direction and reach saturation in the opposite direction. And again, if I come back in the positive direction, it will again go up. And this phenomenon gives rise to the what is called hysteresis. And this is responsible for one of the two important sources of losses in a motor, which is called the steel loss. And within steel loss, we have 2 or 3 different categories of steel loss. We'll look at them in detail. One of them, a significant one, is hysteresis. And next, I will look at something called flux linkage. Till now, we saw flux phi. But the phi, when it is flowing, it is, so to speak, wrapping around the coils. And the coil has n turns. That means the flux is enveloping n turns. And we are interested in the total envelope of the flux, which means we are interested in the flux multiplied by n. And there is a term for it, and that's called the flux linkage. Why this is important, we will see later. It's because that is what defines the behavior of the motor as given by Faraday's law. In Faraday's law, a voltage will get generated which is proportional to the flux linkage. And now, the other important, interesting thing that I want you to note is that if I substitute in the above equation, which is phi into r equals f, here if I substitute for phi by putting xi by n, then the equation changes like this. I get an n squared. The thing that comes after n squared is the reciprocal of reluctance, and there is a name for it that's called the permeance. But since this n squared appears together with the permeance, the whole thing together is called the inductance. N squared into the permeance is called the inductance. And this inductance interacts with the xi. And you will see that the entire motor's behavior is driven by this when we study later. So the xi equals Li. This is a very important relationship I want you all to remember. And permeance, the unit of it is Henry. Inductance also has the same units because it is just multiplied by n squared, which is a dimensionless number. Now, I can again plot, since xi equals Li has a form very much like Ohm's law. I can again plot another curve which shows how the flux linkage changes with current. And here also you find that just like you saw with B and H for magnetic steel, the curve here also is not linear. It is initially very high, and then later on it tapers off in such a way that the inductance becomes very poor. And this will also affect torque production in the motor. We will discuss that later, but I wanted to keep this in mind. So the flux linkage also saturates beyond a certain amount of flux linkage. And finally, we look at the flow of heat. Again, heat that is flowing is in joules per second, also called watts, and that is the thing that is flowing. So it is equivalent to current in electricity. We call it the heat current. And the thing that causes the heat to flow is the difference in temperature, just like difference in potential or the voltage. And the medium in between offers a certain resistance to the flow of heat. So you have an equation very similar to the Ohm's law again. Q is equal to delta T by R. And since Q is in watts and delta T is the temperature difference in Kelvin, the units of R will be Kelvin per watt. And the simplest form of heat flow is across a slab of uniform area, and heat is flowing from left to right. Therefore, you can directly say that the temperature on the left is more than the temperature on the right, and the resistance offered by the slab is equal to 1 by lambda into L by A, which is again the familiar form like 1 by sigma into L by A for electrical resistance, and this lambda is called the thermal conductivity. And as you can see from just a dimensional examination of the equation, the units of lambda will be watts per meter Kelvin. And there is another form of heat transfer, which is called convection, which happens when there is a fluid all around a hot body. The only difference between convection and conduction, as you can see here, is that there is no defined length across which the heat transfer happens. In the case of conduction, it is happening through a finite length called L. But here there is no such length. It is just that all around air is at an ambient temperature denoted by T infinity, and there is a hot object whose temperature at the surface is Ts. So if Ts is greater than the ambient temperature, then heat will just be removed by the air. So the equation is similar to what you saw for the conduction, except that instead of lambda, you have a mysterious term called H. We will look at that in greater detail later. But instead of L by A, you have just 1 by A. So the dimension of L, which is missing in this equation, is absorbed by the heat transfer coefficient H, and you get watts per meter squared Kelvin as a unit. So this is the summary. We have discussed 7 different flows, and we'll be using most of them. We will probably not use fluid in today's discussion, but if we are doing liquid cooling of a motor, then fluid flow also will become important, but I am not covering that today. But all other flows have a very definite impact on the functioning of the motor, and I'll be actually taking you through a workshop like exercise where you can play with all these flows and see how the behavior of the motor is impacted by it. So are there any questions so far? Neetu, do you find any questions?
Nothing on the chat window.
No questions? Neetu, I'm waiting for your response.
No questions on the chat window, sir.
Okay.
To see if somebody wanted to ask it live.
Okay. So do you have any questions to ask the participants?
So apparently only you can do the polls. I wouldn't be able to, but I think I can share the.
You can share, right?
No, I can share the assignment document, and maybe you can create a small poll with just A, B, C, D as options, so they can answer.
Yeah.
Yeah, I'll share the assignment document.
Yeah. So I need to stop sharing so so that you can share?
No. I'm just sharing a Word document, not a screen.
Are you sharing?
1 second.
And all of you, if you have any questions so far, please feel free to ask. I'm seeing somebody say on the chat window that they're not able to submit the poll. I think right now there's no poll yet. The poll feature is becoming very tedious. Neetu?
No problem, sir. In between, if participants have any question, they can unmute their mic and they can ask. But
No, we want to ask. We want to ask
questions.
questions. No, we want to ask a lot of questions because this is not supposed to be a talking session. But there is no way of doing that unless the poll works properly. So this is a problem in this medium. So are you able to share the screen, Neetu? You can first share the screen, then figure out the poll.
No, I wouldn't be able to do the polls. Only you will be able to do the polls. So what I thought was, actually, I have emailed to you a Word document with each assignment on 1 page. So can you pull that up and we can start a simple poll with just A, B, C, D as options, so they will be able to answer. Look at the question on the screen and answer on the poll.
Fine. Okay. Let me just open that document and I can end up sharing it. And as we progress later, Neetu, you should probably let me know when I should stop for posing questions. Okay. So here is the question for all of you. Oops, wait. So are you all able to see this? Do I need to zoom? Oops. So can you all see the question clearly?
So, yes, sir, it is clear.
So Neetu, you are creating a poll. You can all select A, B, C, D.
So I cannot create a poll, sir. Only you can. So you can start a simple poll with just A, B, C, D as options. You'll be able to see the question here, but A, B or C, D on the poll window.
Fine, but then I will have to
start a new poll.
I have to move to a different window. Are you all still seeing the question or not?
No, the question window.
Are you able to see the question or you're not? You're seeing my screen?
No, now question has gone. Now only other window is.
We can see, sir. We can see.
There's actually a very messy. I have to stop sharing if I want to come back to the other window. There's no other way for me to get there.
There is a share button at the bottom. So instead of sharing, so there is a share file option. Can you try that? At the bottom, next to the mute and video buttons, there's a share file option. If you share the file, everybody will be able to see the file.
If I share a file.
Yes, the Word document.
Okay. Yeah, I have shared the file, but now I cannot go back to the
poll
window, to the poll window. How do I go to the poll window now? I can't do that without leaving this. I can't do it. No, I'll have to stop the sharing and only then I can exit. So it's a very messy user interface. WebEx. And how do I manage the time for which the thing shows up?
Paul, there is a timer above.
Wait, I seem to have. So, new poll. The entire thing is very, very unintuitive. The interface. I don't have the option to go to a new poll. I'm just not getting it. I'm still stuck with the old poll. Nothing else happens. There's no way of getting out of it. Okay, I can maybe edit question. No, nothing works. Poll doesn't work. Nope. The entire thing is unresponsive. No. No. Okay. So, A, B, C, and D. Okay. Before I open the poll, how do I set the time? Because it's taking interminably long for a poll to last. I don't know that. Maybe there is something in the options. Display
Timer
alarm,
in
it
the
says 5
options.
minutes. 5
You
minutes
can
is
change
too
that
long.
to. You can change that to.
I can change it to 0.25 minutes. Okay. And open the poll. Okay, I've given you a poll now. A, B, C, D. You can pick any of the four choices that you saw. Let me show back the question again. I don't know if I show you the question whether the window will go.
But the poll has ended.
Oh, has the poll ended? Okay,
That was
I'll be just reposting the same poll again and again, so it doesn't matter. So here's the questions. Have you all seen the question?
you not see the
Yeah,
question
Nick.
anymore. You're not sharing the.
Oh, it's not getting shared?
No.
Oh. Now it's visible?
Yes. And the
And
time is at
is the
15 seconds.
Is the poll visible?
No, because you set the time to 15 seconds. So once you change the timing.
Okay. Let me repost it with a longer time, but then I have to again do this mess of stopping to share. I think just navigating this interface is going to eat up all our time. Such a mess. Sharing. So, how can I edit questions? Yes. No. Okay, I'll make the option as 1 minute. 1 minute. Okay. You have 1 minute to answer this question. I'm opening the poll and I'm sharing the screen. Oh, when the poll is on, it's not sharing. Ah, it's sharing. Okay. So is the poll also on?
Yes.
Okay. And is there a timer coming with the poll? No.
Yes. Yeah, there's a timer.
So all of you can post your answers. Is the time over for the poll or not? Okay, it says 17 seconds.
It ended.
No, 10 more seconds it tells me. 9, 8, 7, 6. Okay.
So some of the attendees are saying they are not able to attend the poll options or poll not visible.
What?
Some of the attendees are saying they either couldn't see the poll or able to click the poll options or poll ended. So I think you shouldn't set a timer. You should just close the poll when you are ready after giving a bit time.
I don't think I can manually close. Last time that's what I did, it didn't work.
No, I meant leave it at 5 minutes or an extended time, but just close the poll when you are ready.
Okay.
But they have not been able to see it or click on it before.
So we have 62 people with no answer, and 14 people have chosen B, 6 people have chosen C as the answer, and 6 people have chosen A as the answer. And which is the correct answer, Neetu, to the question? Let me share the screen again.
The answer is B.
Second choice?
Yes.
Okay, so I think majority of the people have chosen that as the answer. Actually, the question is pretty simple. Because there are 3 pipes in series, the total resistance will be 5 plus 7 plus 2, which is 14. And the difference in the head is 6, 8 minus 2, because the 2 are facing each other. So the flow will be equal to 6 divided by 14, which is 3 by 7. So the pressure drop in each of the pipe will be 3 by 7 multiplied by the respective resistances. Okay. Is there a next question in this? I'll be shooting many questions. I will want you all to answer quickly. I will again activate the same poll. You can all see the question. Is the question visible, Neetu?
Yes, sir.
So shall I stop the sharing and then go on to the poll? Oh. Again, I'll give a 1 minute window, and I would like you all to post your choices.
Sir, please share the question.
Okay, the poll has ended, but I can share the question again.
Sir, we could not see the question as well as the
Yeah. Yeah, this thing is not responding. Till the poll ends, it will not allow me to share. That seems to be the problem.
Sir, actually, the question was not visible at the time when I was trying to solve the question.
Okay, let me share it again. Here it is.
Yeah, now is it visible? Now the time has been, now remaining time is 0. Now it has crossed the limit. So I'm not able to answer then.
Okay,
Yeah,
you can post your answer in the chat.
Okay, sir.
Okay, you should keep the time limit as 5 minutes or 10 minutes or just an extended time limit. And when you're ready, you can just close the poll manually.
Yeah, the problem is the poll doesn't seem to run in the background. I cannot show the screen when the poll is running.
Oh, okay.
It's a very
So
crappy interface.
we are trying to send this document to all the attendees so they can actually pull up on their screen and just attend the call. So once that works,
Yeah, that will be a good
I'll let you
thing.
know.
Yeah, that may be a good thing.
Yeah, but once we are able to do that, I'll let you know.
Yeah. So can I stop sharing this? And I will look at the poll results. Majority of the people seem to have picked B. And if I come back to sharing and look at the screen, Neetu, what's the correct answer? Okay, this is actually a trivially easy question.
Sir. It's D.
D, yeah. So this pressure head is like a battery, which is connected across A and B. So the resistance here is 0, resistance here is 0. So the potential drop between A and B is 8. And according to Kirchhoff's second law, if it is 8 along one path, it will be 8 along every other path. So answer is D. It's a very straightforward question. And I'm finding that the overhead of this WebEx interface is just way too much of this sharing, unsharing, and all that. It's taking up a lot of time. Are you able to see a different screen now? Can you see the PPT now? Or are you seeing only the Word document now?
So now the PPT is visible.
Okay, good. So, well, I think we are progressing very slowly. What do you think about the pace at which we are covering? Are we covering too slowly or are we covering it at the right pace? So far, you can speak and tell me, or you can put your opinions on the chat window. Neetu, you can see in the chat window. Are we going too fast? Are we going too slow? Are we going at the right pace? I think we are going too slow because we are running out of time. Okay. Yeah, the interface is a problem. I agree.
So, so we have emailed this assignment document to all.
Okay. So all of you have got the questions by email. So hereafter, I will not have to share that screen. We'll just do the polling. No. So let me go on to the next section where we talk about power and energy. All of you are familiar that voltage into current is power. In fact, for all the 7 flows that we saw, the flow parameter and the field parameter. The flow parameter is the thing that is flowing, and the field parameter is the thing that is causing the flow. In the case of electricity, the field parameter is voltage and the flow parameter is current. The product of the two is always some measure of energy. Okay. So in this case, it is energy per unit time, V into I. In the case of B and H that you saw, along with the hysteresis curve and other things, the product of B and H is the energy per unit volume and all that. So this is another thing that you can remember, that when you multiply the field and the flow parameters, what you get will be some way or the other related to some energy. So what we supply to a motor is electrical power, which will be equal to V into I. And since Ohm's law tells us that V is equal to I into R, we can also say that power is V squared by R or I squared R. They're all equally valid ways of expressing the same thing. And if voltage and current are not constant, if they are changing, then at every instant we can find what is the power and then multiply it by the interval of time. And if we add it all up, we get the energy. That is what is given in the equation below, that E is equal to integral of P dt. Now, what happens in the motor is that this electrical power input gets converted into a mechanical power output. And the mechanical power will overcome various drag components. I'll tell you in a minute what the drag components are. And finally, after that, whatever is left will result in acceleration. So we can look at the vehicle itself, and we can say that the power is translational power, so it is equal to force into velocity, and the force itself is equal to m into a. The force that we're talking about is what is coming from the motor minus all the losses that are encountered along the way. Alternately, we can look at the shaft of the wheel and we can say it is rotational power. So then the mechanical power output will be torque into angular speed. Torque is analogous to force and angular speed is analogous to velocity. And torque in turn is the product of I and alpha, where I is the moment of inertia and alpha is the angular acceleration. These are all things that you must be familiar with. The important thing is that the final force or torque that we talk about is after deducting all the drag. And typically in a vehicle, there are three kinds of things that eat into the torque available. So one is the rolling resistance, which is like friction, and another is the air drag, and lastly it is the torque consumed in climbing a gradient. So I'm coming now to a very important concept called regeneration. If I take a snapshot of let us say a truck going up a flyover, it is going up a flyover, so it is not going too fast, it's going at a moderate speed because it has to climb. And at that moment, if I see what are the different claimants to the torque, the motor is delivering a certain amount of torque, it's an electric truck, and the total torque delivered by the motor is consumed by different entities in the truck. And you will find that a small amount of it is taken by rolling resistance, a little more is taken by air drag. Climbing is a very big torque guzzler. And finally, what is left is resulting in the acceleration of the vehicle, means its speed will increase. Now, what I want you to observe about these four claimants to the torque is that some of them are dissipative. Dissipative means they result in immediate loss of energy because it just gets dissipated as heat. And that is air drag and rolling resistance. The air drag will just result in the air around the vehicle becoming a little warmer and flying away. And the rolling resistance will result in the tires and the road becoming a little warmer. But you cannot capture that energy back again, permanently gone. But if you look at the torque consumed in climbing, it is resulting in the vehicle going to a higher level. So it's actually stored like as a potential energy. So after the truck reaches the top of the flyover, if he were to stop and switch off the vehicle, then simply because of the height, the potential energy, it will accelerate all the way down. So that is proof that the energy is not lost. It is still stored in the vehicle. Likewise, the acceleration results in an increase in speed after the vehicle has reached a certain high speed. If he were to switch off the engine, means switch off the motor, in our case, our engine is a motor, the vehicle will continue of its own speed for a long distance before it comes to a stop because of air drag and rolling resistance. So that energy is stored in the vehicle in the form of kinetic energy. So acceleration and climbing, which are the two important consumers of the torque, are actually not wasting it, but they are more like a savings bank, where the energy taken from the battery is actually stored in some other form in the vehicle. Now the problem with this stored energy is that if I simply switch off the vehicle and try to run the vehicle using the stored energy, then I will not have any control over the vehicle. The vehicle may not run as fast or as slow as I want it. It will run because of its own dynamics, and that is not something I like. So what I will prefer is if I can take all that energy and put it back into the battery, from where I can take it back again when I want it, in the manner I want it, at the rate at which I want it. So this is called regeneration. How we do it is that when the vehicle is going down slope, or when the vehicle needs to slow down from a high speed, when I apply a brake, rather than applying a normal frictional brake, what I will do is I will make the vehicle drive the motor. When I say make the vehicle drive the motor, it is a torque reversal. It is not that the motor is or the vehicle is rotating in the reverse direction. It is only the torque that is getting reversed. And this reversal of torque will make the motor behave like a generator, and instead of consuming energy from the battery, it will put the electricity back into the battery. And then I can use it whenever I want, in the manner I want. So this will bring down the overall energy consumption and extend the range of the battery for the vehicle. So this is the concept behind regeneration. It's a very important concept, so I spent a little bit time on this. I will not go over these things.
Do you have assignment questions you want to ask today?
Okay, there are some assignment questions. You want to pause for that, or I'll finish this and then we can go on to the assignment. So this is the sequence of electrical to mechanical conversion that happens. The input power, electrical, gets converted into rotational mechanical power at the motor end, and the rotational power then actually gets transformed by something called the gearbox, which can be called a speed reducer. It can also be called a torque multiplier, and the ratio in which it does either of these things is denoted by the number G, which is a gear ratio. So at the other end of the gearbox, you have a different pair of torque and speed coming out, and then finally that torque gets applied to the wheel of the vehicle and results in translational motion, where the torque results in a linear force and the angular speed results in a linear velocity. And all along the way there are losses. There is loss due to the current flowing in the copper. Though the resistance is very low, it's an important contributor to the loss, and that is equal to I squared R. And then there is steel loss, which we already discussed, hysteresis. There is another kind of loss which is even more significant called eddy current, which we will discuss later. And on the whole, we can approximately say that the steel loss is proportional to the square of the speed. And you will see later that the current is proportional to the torque, and the copper loss is proportional to the square of the current. So if you are operating the motor in an environment or in an operating condition where the torque is high, you can expect that the current will be high and therefore the copper loss will be high. If you are operating the motor in an operating condition where the torque is not high but the speed is very high, then the copper loss will be low, but you can expect the steel loss to be very high. And then there are many other minor losses. There is something called skin effect losses in the wire because of AC current, and there is a magnet loss, there is windage loss, there are many things. The output useful power I get will be after all the losses are taken out of the input power. And the ratio between the useful output and the input power that I'm providing is called the efficiency. Since losses can never be eliminated, efficiency will be always less than 100%. And then there is the gearbox. There also there is an efficiency that will come into play. The gear ratio is something which comes from just the geometry of the gears. So we call that a kinematic relationship. The output speed of the gearbox to the input speed of the gearbox, the ratio depends only on the geometry. And so you can see omega prime is equal to omega by the gear ratio. This is because it's only a kinematic quantity. No forces are involved in this. Gear efficiency can be anything between 80% to 95%. Just to be on the safer side, I'm assuming it is 80%. Just to be conservative in my estimation. But you will see that because gear has an efficiency associated with it, which means the output power, tau prime into omega prime, is less than the input power. Therefore, the impact of efficiency is entirely on the torque. If the efficiency is 80%, then the torque becomes 80% because the omega term is unaffected by the efficiency. And then the output torque, which is tau prime, that divided by the radius will be the force, translational force acting on the shaft of the vehicle, and the linear speed of the vehicle will be the angular speed of the output shaft multiplied by the radius. So these are all part of the assignments. We'll not go into this now. If we want to go into the assignment, I'm just looking at the time. I will suggest that you all perform the assignments and we can review that tomorrow. Before I sign off, I will just share one of the Excel sheets that I had sent by email earlier, because that is relevant to whatever we have so far covered. You can open it in your, the name of the thing is called Motor Spec Calculator. You all have it with you already. You can open that. So, would you like me to share it? I can do that. So, can you all see this? Is the screen visible, Neetu?
Yes, sir.
So, somebody came to me about a week ago and said they want me to develop a motor for an electric auto. What you see here is e-auto. And I asked him what the vehicle specifications are, which is what is given here. The gross vehicle weight. See, when we say the word gross vehicle weight, it is including the empty vehicle plus all the people and the luggage that will go into it. That's called the gross vehicle weight. The empty vehicle weight is called the curb weight, KERB, curb weight, and the additional load that it is designed to carry, whether it is people or luggage, that is called the payload. So these are three terms I wanted to remember. Curb weight plus payload is equal to the gross vehicle weight, and the gross vehicle weight is 730 kilograms. Then the wheel radius, gear ratio, the gear efficiency, they have measured it. Whoever came to me has measured the gear efficiency in their vehicle, and they have told me it is 92%. And the drag coefficient is again something that they have done some simulations called CFD. I don't know if you have heard the word CFD, computational fluid dynamics. So they have done some modeling, finite element, and found that it is 0.45. And the rolling resistance coefficient, which is like mu, where friction force is equal to mu mg, that is 0.015. These are all the things that we know about the vehicle, and they want to be able to achieve an accelerator. Actually, this max speed I'll remove. I'll delete that term. You can also delete it. The max speed should not be there. From rest to 40 kilometers per hour, they want to achieve in 10 seconds. That's what this is. And there are two kinds of slope related tests or specifications that a vehicle will have. One is if it is at rest, just to get out and start moving, what is the maximum slope at which it can do? And that requirement is 10.5 degrees. For example, it may be that it is in a basement parking area where there is a steep ramp, or it is maybe the wheel has just got stuck in a pit, and from the pit to just come out, it's like a steep step. It has to get out of it. All of these are times when at almost zero speed or very low speed, I have to apply a steep torque to get out of a sharp gradient, and that is 10.5 degrees. The climbing torque is if I'm going up a hilly road, which I may be going on for 1 hour, 2 hours, long time. Whereas this 10.5 degrees that I've shown here is just for a few seconds. I'll just get out and then I'm fine. Maybe 5 seconds, 7 seconds, typically not more than 10 seconds. Whereas this climbing requirement, performance requirement, is something which will last for hours. I may be going all the way from a low-lying area to a town which is on top of a hill. So that slope they require is 7 degrees. And they want that slope to be climbed at a speed of 15 kilometers per hour, up to 15 kilometers per hour. And on a level road, the maximum speed in kilometers per hour is 55 kmph. Now, if we know all of this, from this I can derive the motor specification, which is what I want to show you how I'm doing. I'm also using a couple of general constants, air density and acceleration due to gravity. So I told you that there are 4 claimants to the torque. The first claimant is the rolling resistance. So it is, I'm just writing here so you can see, the first claimant to the torque is mu into m into g. This is the frictional force, and if I am on a slope, it will be mu into m into g into cos theta. If I'm on a level road, theta will be 0, so cos theta will be 1. So the term will go away. This is the rolling resistance. And the second claimant to the thing is air drag. It is half into rho, which is the density of air, into CD, which is the drag coefficient. You can see the formula here. Half into rho into drag coefficient into, what is the D7? Into area into V squared. Okay. drag coefficient into area into V squared to the formula. And the third claimant is the climbing, and that will be equal to M into G into sin theta. So in all the different operating conditions, all of these forces will eat away the torque. And finally, whatever I'm left with, if I add all of this and say this is the total drag, then if I subtract this total drag from the force that I'm getting from the motor, what I'm left after subtracting will contribute to acceleration. So the force that is remaining will be equal to mass into acceleration. So with this background, I want you all to figure out each of the different conditions that the customer has given on the left hand side of performance, acceleration, other things. I have used that to derive the specifications of the motor, the torque, speed and power for each of the conditions, and I have used this understanding to then plot speed versus, if we zoom out a bit, yeah, I have plotted from the requirements I have derived the specs of the motor, and what you see here as the blue line is what comes from the calculations from the specs, and whatever is a very short term requirement of very high torque, that is called a peak torque, we can exclude that from the normal specification of the motor. I'll discuss about it later. And whatever else is required as the torque on a continuous basis will be the what is called the rated torque of the motor. So using this blue line, which comes from the customer requirements, I have derived this dotted gray line, which is the torque speed curve of the motor, and that speed continues up to 3500 rpm approximately, and afterwards it falls to a very low value of 4 Newton meter at close to 5000 rpm. So this is the torque speed curve of the motor that we should be designing, and this torque is plotted with respect to the speed, and the product of the torque and the speed, remember the speed is in rotations per minute, I have to multiply it by 2 pi by 60 to convert it to radians per second. If I do that and then multiply it by the torque, then I will get what is called the power. Torque into angular speed is the power. So I can plot the power also with respect to the speed. So I will urge you all to review this Excel sheet and you will understand all the calculations. They are very simple. They are all just some different ways of saying F is equal to ma. There is nothing more complicated than that. But as you can see, we have already designed the motor. Just from a customer's requirement, we have published an important part of the data sheet of the motor, which we are yet to design. That's how powerful the idea is. So just remember this. If you have not already noted it down, I will urge you to quickly make notes of it. Of course, if you don't, you can always pick the cells and you will get the formulas there. But this is a formula on the basis of which all these things have been calculated. And I think we are running out of time. So tomorrow, what I will do is that I think today we covered 2 out of approximately 10 chapters in the deck. And if we go at that rate, we will not be able to finish anything at all. So tomorrow I plan to not spend more than half an hour in running through the remaining 10 chapters. I will be really zipping through them. I would urge you all to look at the decks at home and look at the videos if you have any doubts. The quick way to cover it will be if you skim through the deck that has been sent to you by email, and wherever you think something is not easy to understand, refer to the video. And there's no point in my repeating whatever is there in the video. I will not do that. So only as a very quick refresher, in less than half an hour, I'm going to cover the remaining 8 chapters, because after that, I will be taking you through a very important Excel sheet, which is called the estimator, and I'll be teaching you how to use this as a tool to do all the calculations. You can do electromagnetic calculations here, and seemingly very complicated things which people normally resort to finite element analysis, you can just get from a very simple straightforward Excel sheet. And you can get steel losses from a separate tab, and that is linked with the electromagnetic tab. You can get all the thermal temperature profile in the thermal graph, in the thermal tab, and the what is called the winding temperature, which is the hottest part of the entire motor. That is also linked with the electromagnetic tab, because you must remember that when the resistance increases, the temperature increases, the electrical resistance also will increase. And when the electrical resistance increases, that will also affect the electromagnetic performance. So all of these are interlinked and looped. And it can be a pretty messy thing, but fortunately, this tool is extremely neatly and systematically organized. I and my team have developed this over the last 2 or 3 months when we were idle during the lockdown, and it's a very powerful and useful tool. So I will be taking you through this, and I want to spend 1 hour at least in walking you through this, because this is a very important tool that will come in useful to you. So I will not be spending more than half an hour on the lectures. I will urge you to go over the lectures and use whatever time we have to ask any doubts and questions, rather than just have me to repeat the lectures that are already recorded on video. And lastly, before signing off, I don't know whether I should take you through this. Maybe it's not necessary. We can cover this tomorrow. Okay.
Sir,
yeah.
some of these, as I was saying, they do not have a link for the videos.
The link for the video has been sent, but the NPTEL link. What happened is, in the original, in the first email that went, the body of the email had a word that linked to the correct link, but in the bottom another wrong link was mentioned. I think somebody has posted on the chat the URL. Thank you, Mr. Vittalani. You had written earlier to me by email also, and I sent you the thing. Fine.
There is also
okay.
someone saying
there's a comment that there's only one sheet in the estimator file. No, I had shared all the 4. There are 4 tabs in the bottom. There is a README, there is an electromagnetic, there is a steel, and it's only one file, but there are 4 tabs. Please check and let me know. Okay, so one response in the chat is that only one tab is there. Okay, somebody else is confirming that there are 4 tabs. No, definitely there are 4 tabs. I just sent them as a zip folder. So probably if you once again download the zip folder and unzip it, you may get it. There may have been some corruption in the download and unzipping process.
Or you might be looking at the motor spec calculator file.
Maybe you're looking at the motor spec calculator that has only one tab. The estimator has 4 tabs. Yes, file named estimator with steel and thermal has 4 tabs. So if you don't have any further questions, I think we are at the end of the time allotted to us. And feel free to, I think you all have my email ID also, right? I can post my email ID here in the chat. Everyone, once again.
Is there any questions you want to interact?
So if you have any questions right away, you can ask. You can also send me questions or send me any feedback on the email ID which I have posted in the chat window. I think chat window is visible for everybody, right?
Yes.
Fine.
Sir,
So I'm done. Yeah.
Questions right now. So thank you, sir. Thank you.
I'm mechanical engineering, right? So where to start? I want to design a four-wheeler for with the help of electric combinations. So where to start, sir?
So the first place to start obviously is by defining what are the performance specs of the vehicle that you want to build. And the Excel sheet that we just now discussed will help you do that. And from that, you can derive the specifications of the motor. So you have not designed a motor, but you have already published the data sheet of the motor from the vehicle requirements. And having done that, how to design the motor itself is what I will be taking you through when I discuss the estimator tomorrow. But you will not understand anything that I do unless you have seen all the videos.
Sure, sir.
So you must see the videos. The quick way, as I told you, is just look at the PDF decks that have been shared. 4 decks have been shared with you. You can run through it. All of you are experienced faculty in different disciplines. So you may find that 60-70% of what is covered is something that is very simple, you already know. There may be some parts which are new and difficult. For those alone, you can refer to the lecture videos and listen to them a little more carefully. So you don't have to listen to all the videos because each video is half an hour long and there are something like 17 of them. You will take 8 hours to listen to all those videos and nobody can absorb so much of information. You will only be fatigued. I won't recommend you do that. You just run through the PDF and dip into videos wherever you need some explanation.
Thank you, sir.
Okay, Mr. Vithalani, I will send you a mail separately with the estimator. I have your mail ID anyway. So I'll send you the estimator separately.
What is the agenda for tomorrow's class, sir?
So tomorrow I told you I'll be spending less than half an hour in running through the remaining 8 chapters, 7 or 8 chapters, I don't remember. We have covered only 2 today. There are additionally some 8 chapters to cover. And after that, I will be walking you through the estimator, which is a tool which I want you to learn how to use in your hands. So just like now there was a question that I want to build a motor, I know what vehicle I want to use it for. How do I go about it? So in that there are 2 steps. From the vehicle's specifications, you derive the motor specifications that we already seen today in the Excel sheet that we discussed now. The second step will be knowing the motor specification. How do I design the motor that runs according to those specifications? So that is where the estimator will be a very valuable and simple tool. If you don't have the estimator, you can of course purchase what are called FEA solvers, finite element analysis solvers. They are very inexpensive, only 35 lakhs. Alternatively, you can learn to use this Excel sheet and do all the design by yourself. So we'll be spending most of the time in discussing the estimator tomorrow. Any other question?
So, is there any questions you want to ask? I think we are done with the session with no questions. Thank you Professor Kannan for addressing us in this
And please go through the assignment also and try to send your answers by email to me or to Neetu. I'll post Neetu's email ID also here. You can send your assignment responses to Neetu, and she will give a feedback on what is correct, what is wrong. She'll give you the solutions. Yeah, over to you, Dr. Anaga.
Yeah, thank you, Neetu, and thank you, Professor Kannan, for addressing us. We have another interesting session tomorrow, Professor Kannan, from 12 p.m. as communicated earlier. So you hope you will come up with more questions and follow us, lectures, and whatever documents you have shared with you, so that it becomes more interesting and you understand the basic concepts of designing the electric vehicle and the motoring part. With this, I would like to thank Professor Kannan and Ms. Neetu for being with us in this session. Thank you, sir. We'll be commencing the next session at 12 p.m. We'll commencing the next session at 12 p.m. Thank you, sir.
Till noon. Yeah. Thank you. Thank you very much.